Hello everyone, welcome to MEC310 Introduction to Machine Design. My name is Nilanjan Chakraborty and I will be the instructor for this course. First of all, I hope that all of you and your loved ones are staying safe and healthy during these times. So as I have already communicated with you, due to the ongoing public health situation, this course will be fully online. So the best mode of communicating with me is through email, and my email ID is given here. It is also present in the syllabus that is uploaded to Blackboard. My office is in the Heavy Engineering building, room 212. However, I will not be holding physical face-to-face meetings during this semester. Office hours and any one-on-one meetings will be held through Zoom. This is the first lecture of this course. So what I will first do is provide you with a course overview and some administrative information. That will be the first module of this lecture. The second module of this lecture will go over the process of machine design. And in the third module, we will start out with the technical material, where I will first present some preliminaries and some terminology. So what is this course about? This course is about fundamental topics in the subject of machine design. So roughly speaking, the idea that we have about a machine is a bunch of rigid objects that are constrained together to move in such a certain way. And either we want to get some more motion out of the machine or we want to get some power out of the machine. And a machine is usually composed of multiple mechanisms. And our goal in this course will be to study analysis of such mechanisms and synthesis of such mechanisms. The purpose of analysis is to study the mechanisms so that we understand their kinematic and dynamic behavior. The purpose of synthesis is kind of the opposite of analysis, where our goal is to essentially accomplish certain desired motions or tasks. So before we go into the details of the course, first I want to talk about the prerequisites. So there are two prerequisites for this course and one core is requisite. MEC102 or knowledge of MATLAB is a prerequisite for the course. The reason is that there will be programming assignments in this course where we will be required to use MATLAB. The second aspect is that this course is about motions of rigid objects. Right? So engineering dynamics or MEC262 is also a prerequisite for the course. MEC203 or knowledge of a CAD software is a co-requisite, and this will be useful to you in your projects. I want to say a few more words about MEC262. What you need to know from MEC262 is velocity, acceleration, and force analysis of a rigid body. You need to know this because these are the fundamentals based on which you will be doing the kinematic and dynamic analysis of machinery. So as I said, I am the instructor. I have also listed my phone number here, but this semester I would not be available by phone. So I would request you to communicate with me through email. The teaching assistant is Wan Liu and her email ID is given here. You can also communicate to her through this email ID. The required text for this class is Design of Machinery by Robert Norton, and we will be using the 6th edition. If you have the 5th edition or the 4th edition, that will also work, but the 6th edition is preferable. As I already told, the lectures will be online, so I will be pre-recording lectures and posting it on YouTube, and the links to the lectures will be posted on Blackboard. So since the lectures will be online and pre-recorded, the class hours will be used as office hours. So I will be holding office hours during our scheduled class hours on Monday and Wednesday between 4 p.m. to 5:30 p.m. Since these are scheduled class hours, I'm hoping that everybody would be available at this time. But I also understand that some of you may not be physically present in campus and maybe living in altogether totally different time zones. For those students, you need to make an appointment with me by email, and we will work out a time if you need any assistance. The Zoom link for the office hours is posted on Blackboard, and if you go to Blackboard and under the MEC310 course, you look at the tab Zoom meeting on the left hand panel, then you will find a list of the meetings, and from there you can just log in. You will need your Stony Brook ID as an authentication mechanism to actually log into Zoom. Now, there is an issue when we do these Zoom meetings, whether you want to do private one-on-one meeting or you are okay with other students also being present during the meeting. If you want private one-on-one time and you don't want other students to be present, you should send me an email in advance so that then I can put others in a separate waiting room probably to make sure that we are in a one-on-one situation. So since this is a new thing for all of us, I'm sure that there may be some issues that may be coming up. And the best way to resolve those issues is through open communication. So just send me email if you need anything or if you think that you want to meet me to discuss a certain issue. So homework. There will be about one homework assignment per week. So it is not exactly one. Sometimes there will be one per 2 weeks. But for each one of the homeworks, you will have about 1 week after it is assigned, and late homework will not be accepted. You have to submit the homeworks through Blackboard. So the homeworks will not be multiple choice type questions. I expect you to write the answers, scan it, and submit the PDFs on Blackboard. And I will accept only PDFs and not JPEG images or things like that, so that there's a uniform way of grading everything. More instructions about the homeworks will be posted when the homeworks are assigned to you. So in total, I expect about 7 or 8 homeworks will be assigned. There will be 2 design projects, and each design project will be due approximately 4 weeks following its assignment. And there is a written report required for each design project. There will be 2 midterms and 1 final exam. The first midterm is tentatively scheduled on October 7th. The second midterm is just before the Thanksgiving break on November 18th. The final exam is scheduled on Wednesday, December 9th between 8:30 p.m. to 11 p.m. All of the exams will be administered online, and they will be scheduled during class hours. However, again, here I understand that there will be time zone issues for some people, and there may be some people who may need extra time for exams. So these exceptions have to be arranged separately, and you need to send me emails if you are in a separate time zone and you cannot be there during the class hours, or you need some accommodations for the exam. So there will be no makeup exam or no accommodations unless it is arranged prior to the exam. So the homeworks will constitute 15% of the grades. The projects will constitute 20%. So 2 projects, each one of them will be 10% of the overall grade. The two exams, the midterms, will contribute 15% each, totally contributing at 30%, and the final comprehensive exam will contribute 35%. The grading scheme, the letter grading scheme is shown here, and it is also given in the syllabus uploaded on Blackboard. I usually follow this. It is usually not a curve, but if it requires to be curved, there have been instances in the past where I have curved the final grades. In addition to the criteria laid down here, there is also a requirement that you have to get a minimum of 60% on each design project for passing. So all homework assignments and solutions will be posted on Blackboard. And I will be using email and Blackboard exclusively to communicate with you. So please make sure that Blackboard is accessible to you and you have a Stony Brook email ID. So academic honesty is always a tricky issue, and it is especially tricky under these circumstances. I would expect you to not copy class assignments or homeworks or exams. That is clearly a violation of the academic honesty principles. Furthermore, using solutions that are available on websites where they pay you for, you have to pay for the solutions, that's also not acceptable. I do encourage students to work with each other, but you have to write out your own solution. You cannot copy from your friends. And as I was stating before, if you need some special accommodation where you'll need more time for the exams, you need to contact the Disability Support Services or DSS, and you also need to email me so that we can have an arrangement that suits your conditions. Okay, now that we have gone over the basic administrative information and course overview, we will now get into an overview of the machine design process. So to start out, what is the meaning of the word design, or where does it come from? So design comes from the Latin word designare, which means to designate or mark out. If you look at a dictionary, you will see that its meaning is stated as to outline or plot an action of or work, or to conceive, invent, and contrive. In terms of machine design or engineering design, what we understand design as is the process of problem solving. More particularly in engineering design, design is the process of applying various techniques and scientific principles for defining a useful device, process, or a system in sufficient detail so as to permit its realization, meaning that it can be manufactured. As a very concrete example of an engineering design problem or a machine design problem, consider the design of a robotic vacuum cleaner. So here, what is the design problem? What you want to do is design a vacuum cleaner that can navigate or move by itself, any house, and collect dirt. And there are already products in the market that kind of attempt to solve this problem. So this is a very concrete engineering design problem. So machine design is a subfield of the field of engineering design. So before we get into the steps involved in machine design, let's first look at a working definition of a machine. To us, roughly speaking, a machine is an apparatus consisting of interrelated units or objects that generate a desired motion pattern and or force or power. And machine design is the process of creating such machinery that functions desirably, safely, and reliably. And as a design engineer, your role will be to define and calculate the motions, forces, and changes in energy of the different parts so as to determine the sizes, shapes, and materials needed for each of the interrelated parts in the machine. For example, if you look at any one of these robotic vacuum cleaners, it will have a body or a structure. It will have a motor. It will have sensors. So there will be different objects or pieces that are embedded into the system. Now, for the rest of the next 2 or 3 slides, to get an overview of the design problem, or more precisely to get an overview of the machine design problem, the actual design problem example that we will look at is that we need a better vacuum cleaner. And the word better, at this point, I am not defining it precisely. Better means something that has capability above and beyond what is there in the current products. So what is the machine design process? Machine design process consists of a number of steps, and these steps need not be done in a linear fashion as listed here. So what I will first do is kind of go through each one of these steps, describe each one of these steps at a high level. Then in the next couple of slides, I will use the example of designing a better vacuum cleaner or a better robotic vacuum cleaner to further explain each one of these steps. So the first step that you have to perform in a machine design process is identification of need, or why do you need that machine. Sometimes you do not need to perform this step. The need may be obvious, or it may be prescribed to you, or it may be given to you. The next step that usually comes up is background research on the actual product. If there are versions of the product that are already there in the market, you want to do some research on that. You want to look at patent filings by others to see if there are patents on the concepts or ideas that you are thinking about. Based on the first 2 steps, the identification of need and the background research, you come up with a goal statement for your design. This is a high-level qualitative statement. Then from this goal statement, you go to specific technical design specification. And this is often numeric in nature. The next step is what is known as the ideation or the invention stage, and it is also known as the stage of conceptual design. So this is a stage where you essentially sketch out different concepts, and then you analyze these different designs. And here you may use scientific tools. Based on the analysis, you select some designs. Then you go on to a detailed design phase. In the detailed design, you essentially choose the material properties of the shapes, all of these things, where your holes will be, so that you can join 2 parts. So all of these things go into the detailed design. After the detailed design, you go through a prototyping and a testing stage. And once all of these things are done, then you go to the production stage. Note that, as I stated before, it is not a linear process. You may jump back and forth. So you may do analysis. So suppose you came to this ideation and convention and invention stage. You did analysis and you found that, okay, none of the ideas that you came up with are good. You can go back here from here. Or you may even want to change your design specification or your goal statement, because it may not be feasible to design what you intend. So I can go back and forth between any one of these steps here. Even after I come to prototyping and testing, I may see, okay, whatever I have designed, that doesn't really work. So I may need to go back to my drawing board, to the ideation stage. So it's an iterative process with a feedback loop. And this is true even you go to the production stage. You go to the production stage and you can see that, okay, whatever you have designed, it is not suitable for maybe mass production. and then you need to go back to either here or maybe even here. So just to make this high-level description more concrete in the context of the problem that we had before, we want to design a better robotic vacuum cleaner. Okay, so what would better mean? So we need to identify that need. What is better? One of the problems with current robotic vacuum cleaners is that they cannot negotiate steps. Your notion of a better vacuum cleaner can be a vacuum cleaner that can negotiate steps. The first step that you will do is collect details about all the robotic vacuum cleaners available in the market, and also see those manufacturers, what are their patents they have filed, so that whenever you do a design, you do not run afoul of those patents. Next, you will make a more precise technical goal statement. For example, the goal statement that I can come up with here is that I want to design a mechanism that can switch between a vacuum cleaning mode and a walking mode for the robotic vacuum cleaner. Once I have this goal statement, this is still at a very high level. I want to make it more precise, and that comes in the next step of the performance or task specification. Here, I want to put in requirements like self-contained power supply, cost maybe some number of dollars, types of surfaces the device should cover, overall dimensions, and all. You can go on and on. The next step would be the ideation and invention step. For example, what type of mechanism should be used here? How many legs do you want to use? 2, 4? This is a step for which we will learn some methods to perform parts of this step. It is not in the context of the robotic vacuum cleaner design problem, but in other contexts. The next step would be to analyze each one of the conceptual designs. And again, we will also learn methods to perform these steps. After that, depending on my metrics and factors like cost, safety, performance, reliability, I will be choosing one design as the best design. And this selection step is usually a trade-off between different factors. So it is a subjective step as to what is important to you, or what do you think would be important to market or sell this product. The next step is the detailed design step, in which you have to specify the dimensions and materials for each part of the machine. Then you go to the prototype and test it extensively, and finally you go to the production step. Among all the steps that were mentioned in the previous 2 slides, there are 2 key steps that I want you to note, and they are present in any machine design process. Those steps are the synthesis of the mechanism or machine and analysis of the mechanism or machine. And usually you have to iterate between these 2 steps. And this is one aspect I really want to emphasize here. In design, you have to always do lots of iterations. Design is inherently an iterative process, and therefore successful solutions to design problems will require skills in both synthesis and analysis. And these will be the 2 main topics that we'll be spending a lot of time on. The types of machines or mechanisms that we'll be emphasizing during this class are 4-bar mechanisms, and we'll be looking at both the synthesis and analysis. We will look at cam profile synthesis, gear train synthesis and analysis, and also force analysis and dynamic balancing of 4-bar mechanisms. So I have been using these 2 words, analysis and synthesis. So let's just take a very high level look at what these 2 terms actually mean. For any given machine, the goal of analysis is to determine the performance of the machine using methods from mathematics and engineering sciences. So this is a very technical step. It is often quantitative in nature, and it involves assigning numerical values to various design parameters. and assessing the resulting performance of the machine. And you will often get a unique or correct solution. So this is a mathematically precise step, usually the step of analysis. You can try to optimize the performance with respect to design parameters. So in this analysis step, you can also choose design parameters so as to improve or optimize the performance of a machine. However, the chosen concept during the synthesis process inherently limits what you can do through the analysis phase, even if you can optimize your design. On the other hand, in synthesis, given a desired task, what we want to do is to determine the structure and dimensions of the machinery so that we can perform the desired task at the desired performance level. It is the creative aspect of the design process, and this is done in many different steps. At the concept generation stage, it is often qualitative. Several design concepts are sketched out and compared before you make a decision. And this synthesis step doesn't have a unique or correct solution. Usually, there are many possible solutions that are acceptable or correct for any given problem, but some solutions can be quantifiably better than others. Any design of a mechanism, even the simplest mechanism, requires several iterations between synthesis and analysis before you obtain a satisfactory design. And this message will be emphasized through the class projects, where you will get a first-hand experience of the iterative nature of design process. So why do we need iterations? At a high level, it is very simply because the chosen concept that you have done basically based on sketching on the back of an envelope or just from your experience and thinking about the problem may not fulfill your design stipulations for reasonable values of the design parameters. Or analysis could suggest that there is an advantageous modification of the design concept. This is often known as guided redesign. So if you search for this term guided redesign, what it basically means is that analysis guided synthesis or analysis guided design. So synthesis is thought by some people to be the glamorous aspect of design or the creative aspect of design, as I also stated. However, if you want to do real-world engineering design, it is often based on modification of existing designs or selection of standard components. Another key point in design is design trade-off, which I had mentioned previously but only briefly. The design of any product has many different design requirements, and these different design requirements often make conflicting demands upon the design process. For example, there is usually a trade-off between quality and cost, strength versus weight. So any practical design is a recent compromise among such conflicting requirements. The two key takeaway messages from our discussion here is that first, design is an iterative process. Second, trade-offs have to be made in selecting the final design. These two aspects of design will be emphasized in the course through the projects. Now we will go over to the next module of this lecture, which is talk about some basic mathematical preliminaries and terminology. At this point, I want you to pause the video for a few seconds and think about the notion of a point mass and a point. Geometrically, what is the example of an object that you can consider as a point? What is the example of an object that you can consider as a point mass? The reason I want you to do this exercise is to realize that there is no such object which is actually a point geometrically, or physically a point mass. The usual definition you see of a point mass is an object whose dimensions are considered to be zero, but it has non-zero mass. And if you think about this definition, this is a paradoxical definition. If you have dimension 0, you cannot really have non-zero mass. So the other way to think about it is that a point mass is an idealization of a physical system where the size of the system is ignored. The basis of Newton's law is the assumption that you are dealing with point mass. And when you have applied Newton's law before, it is not that you required the objects to be point objects. It is simply that the size didn't play a role there. So next comes the notion of a rigid body. A rigid body is a set of points in which the distance between any two given points remains the same irrespective of the external forces exerted on it. Again, there is no physical object that is truly a rigid body. A rigid body is an idealization of a solid. It is an abstraction, it's a concept. You can use it to model solids. And that model goes a long way into describing and predicting the motion of objects. However, it is important to realize that our geometric notions of point, line, circle, triangle, square, cube, sphere, these are all idealized notions or abstractions. Physical objects can be approximated or modeled by these abstractions. No physical object is actually a cube or a sphere. It is only approximately a cube or a sphere. Similarly, as I have already stated, no physical object is a point mass or no physical object is a rigid body. You model a physical object as a point mass when the size of the system can be ignored. You model a physical object as a rigid body when the size cannot be ignored, but the deformation of the object can be ignored. The reason I am talking about this separation of the idealization of or abstraction of objects from the actual objects themselves is because this idea will be useful to us in studying mechanisms and machines. We will define two new idealizations or abstractions, which will be links and joints. These links and joints will have their physical realizations. However, they are essentially abstract notions, as we will see in the next few slides and later throughout the course. Since we are interested in studying motion of an object, the first thing that we need to understand is the notion of degrees of freedom. So if I have a point mass, what is the degree of freedom of a point mass? It is the number of independent parameters required to describe a point. So how do you describe a point? You have a coordinate system or a reference frame, and a point in this reference frame, one way of describing it is by its x and y coordinates, and that's in the plane. So you need two parameters to describe the position of a point in the plane. So the degree of freedom of the point is 2. In 3D space, you need 3 parameters to describe a point. So in 3D space, the degree of freedom is 3. The 3 parameters, one way of describing this is x, y, z, the coordinates of the point. When we move to a rigid body, the definition of degree of freedom is similar. The degree of freedom of a rigid body is the number of independent parameters, and I have highlighted independent parameters here because the term independent is important. That is required to describe the body. If I consider a rigid body in the plane, capital X, capital Y here is my world reference frame. What I will do is also attach a reference frame with the body, and I will write it as xb and yb. So this rigid object can be described by the position of the origin of the frame B, which is the point A here, and this angle theta. So you need three parameters here: xa, ya, and theta. So the degree of freedom of a rigid body in the plane is 3. Now there is one aspect here which I haven't really made clear, which is what does it mean to describe a body? What it means to describe a body is that given the position of any point on the body in the body frame, you should be able to describe it in the world frame. And if you know the parameters xa, ya, and theta, you will be able to do that. At this point, I am not showing it mathematically why this is true. We will see this later in the class. At this point, what I want you to realize is that the degree of freedom of a planar rigid body is 3. If a rigid body is moving in 3D space, then its degree of freedom is 6. In this course, we will be mainly concerned with planar motions of rigid bodies. We will not be concerned with spatial motions. So what are the types of planar motions that are there? So planar motions can be pure rotations, pure translations, or general planar motions that consists of both rotations and translations. In pure rotation, there is always a fixed point which is called the center of rotation, and the paths of all points in the body form concentric circles with its center at the center of rotation. Note that the center of rotation need not be on the body itself. It can be outside the body, but it will be a point on the plane. In a pure translation, the orientation of any line within the rigid body does not change. What that means is that at any instant, all points of the body has the same velocity. Or there is another way you can think about pure translation. It's a rotational motion where the center of rotation is at infinity. A general planar motion is a complex motion that consists of both rotation and translation. However, as you have studied earlier, that any general planar motion can be thought of instantaneously as a pure rotation about an instantaneous center of rotation. The difference between pure rotation and general planar motion is that the instantaneous center of rotation is always constant in pure rotation. It does not change with time. Whereas in general planar motion, the instantaneous center of rotation is changing with time. We will now go over some basic terminologies that are used in mechanics. So the study of mechanics is usually divided into two parts: statics and dynamics. Statics is essentially the study of equilibrium of forces. Dynamics, on the other hand, is the study of motion. Dynamics is further subdivided into kinematics and kinetics. In kinematics, we study motion, that is, change of position, velocity, acceleration, without any regard to the cause that is creating the motion. And in kinetics, we study the relationship between the motion and force. This distinction is classical and I believe was proposed by Euler. In modern parlance, many authors distinguish between kinematics and they conflate the term dynamics and kinetics. And we will be doing the same sometimes in this class. So the use of the word kinetics in many places is out of vogue or out of fashion. People usually use kinematics or dynamics. When they use kinematics, they mean study of just motion without regard to force. And when they use dynamics, them in study of motion along with force. As I just stated, kinematics is the geometry of pure motion. It deals with relative motion between rigid bodies without the consideration of force or mass. This is a useful concept because this will help us define a mechanism. A mechanism is a mechanical device used to transmit only motion without reference to force or mass. What are some examples? A camera shutter, an analog clock, a folding chair, or an umbrella. In all of these cases, what you are interested is in the final position or in the motion of the object. You are not considering the force that is being transmitted. That is not of importance to you. Of course, without force, we cannot have motion. However, the key point is that the force transmitted is not of interest. What is of interest is the final motion. And as we just discussed, kinetics is the study of forces on systems in motion, and we distinguish between a machine and a mechanism. A mechanical device used to transmit both motion and force or power is called a machine. So when we talk about a machine, we are thinking about both motion and power. For example, you can think of a food blender, an automobile transmission, a bulldozer, a robot, an amusement park ride. Here both the force that is transmitted and the motion, both of them are of interest to us. So usually we have the terminology that we are studying kinematics of mechanisms versus dynamics of machines. And this terminology comes about because we think about mechanisms as a device for which motion is only important, whereas machines as a device for which both motion and force are important. That being said, kinematics and dynamics are not physically separable. This separation that I'm talking about is mainly conceptual or for studying. Acceleration, which is a kinematic quantity, and force, which is important in dynamics, is related by Newton's second law. You cannot have acceleration or motion without force. However, in engineering design, it is a valid and common practice to consider motion at first and then consider the force associated with the motion. And this is also the principle that we'll be using throughout the class. We'll be first studying motion, and near the end of the class, we'll be considering forces that arise due to the motion or that are required to make that motion possible. So in kinematics, as used in mechanisms, what we do is first we design the desired motions of the mechanical parts that we are interested in. And then we mathematically compute the positions, velocities, and accelerations that these desired motions will create on the other parts. At a high level, we want to generate the desired general motion scheme. And then we want to figure out the details of motion of each component part. Once we have studied the motion, of which acceleration is one output, from the acceleration we can determine the forces required to get that motion, and from the forces we can determine the stresses that will be coming on the parts, which is required for the detailed design part. So the steps are, first we do kinematic analysis, then we do dynamic analysis, and then we do stress analysis. Stress analysis is not a part of this course. We will only do kinematic analysis and dynamic analysis. There is another term that is frequently used, which is a kinematic chain. A kinematic chain is an assemblage of links and joints, and they are interconnected in a way so as to provide a controlled output motion in response to a supplied input motion. So the key features are that there are rigid bodies or links that are connected to each other by joints. For example, if you think of the door in your house, any door in your house or in your room, it is an example of a kinematic chain. Okay? There is a hinge joint and there is the body of the door. And the hinge joint is constraining the motion of the door. You supply an input motion at the handle of the door and there is a controlled output motion. The door opens. So a kinematic chain can be open or closed. For example, a robot arm or your arm by itself. It is an example of a kinematic chain that is open. An example of a kinematic chain that is closed is a crane. A mechanism is a closed kinematic chain in which at least one link has been grounded. So this notion of grounded is very important. Grounded may sometimes mean that the link is fixed, that it is not moving, which is the usual meaning of ground, that it is something that is fixed and not moving. However, more generally and more precisely, if a link is grounded doesn't mean that it is fixed. It may itself be in motion. The grounded link may be in motion. The key aspect is that the motion of the rest of the rigid bodies or links in the kinematic chain is studied with respect to the grounded link or with respect to a reference frame attached to the grounded link and moving with the grounded link. So this notion of grounded or fixed link is something that we will again revisit later in the class. However, at this point, what I want you to note is the difference between a kinematic chain and a mechanism. A kinematic chain is just a connection of rigid bodies with joints. A mechanism requires that one of the links of the kinematic chain be grounded, or we choose one reference frame and then we say that we will study the motion of all the bodies with respect to the reference frame attached to this particular link that we have fixed or chosen. So let's now go into some examples of kinematic mechanism. As I already told you, a mechanism transmits only motion without reference to force or mass. There are other authors which have provided other definitions, but they are kind of similar in spirit. So according to Hunt, a mechanism is a system of elements arranged to transmit, control, or constrain relative movement between objects. The figure on the left is the slider crank mechanism, which is a mechanism present in the IC engines of your cars. The figure on the right is a Geneva mechanism, which is present in analog clocks. What this mechanism is doing is transforming an input continuous rotational motion to an output discrete rotational motion. And again, here this discrete motion is of importance to us, not the actual force used to create this discrete motion. The way a slider crank mechanism works can be seen here, and you can see that there are multiple moving parts and these parts are moving with relative to each other. There is the cylinder and the piston is moving relative to the cylinder. So there is a joint between this piston and the cylinder. Similarly, the yellow link here is called the crank and the white link here is called the connecting rod, and the crank and the connecting rod are constrained to have a relative rotation between each other. This is the mechanism that we will be studying in quite a bit of detail. Next, we have a 4-bar mechanism. This will be our canonical mechanism that we will be studying. We call it a 4-bar mechanism because there are 4 links: the green link, the red link, the blue link, and the ground link, which is this connection here. Although there is no physical bar present there. That is why I told you before, you have to think about a link as an idealization of a physical object. So here there is actually just the support on which this mechanism is resting. However, you consider a link as the line connecting these two fixed pivots or the revolute joints. So you can see that there is a relative motion between the parts that is generated by rotating the green crank. And the motion here is quite complex. If you have seen the previous slide, the motion between the cylinder and the piston was translational. The one before, in the Geneva mechanism, the motion between the input and the output, it was just rotational, pure rotational. So pure rotational, pure translational, and complex motion for the 4-bar mechanism. And when I say complex motion, I mean complex motion of this red link here. The green link and the blue link are undergoing pure rotation. As I said, that in this class we will be studying planar mechanisms. However, there are other types of mechanisms that we should at least have some idea about. So let me just first define planar mechanisms in a little bit of a formal way. So when all links move in parallel planes or in the same plane, we obtain a planar mechanism. And note, parallel planes is important here. Planar doesn't mean that the links will be moving in the same plane. Because if you think of it, if the links move in the same plane, they will collide with each other. Physically, it may not be possible for links to move in the same plane. However, in general, a mechanism generates a 3D motion, and it is called a spatial mechanism. So the picture on the left is an example of a spatial mechanism, which is a 6 degree of freedom Stewart platform or Stewart-Goff platform. So this plate on the top can change its position as well as orientation. And this is a mechanism that is used in flight simulators. So the person will be sitting on top of this platform, and this platform will be moved around to simulate the effect of flight. Now there is another special type of mechanism which is called a spherical mechanism. It is a part of spatial mechanism, but it is special in the following sense, that all links will be rotating about a fixed point. This distinction is important because it may be easier to design spherical mechanism compared to a general spatial mechanism. However, as I stated, this course deals only with planar mechanism. So this is the end of lecture 1. In the next lecture, we will study in more detail about mechanisms. We'll get into more detail about links and joints, the types of joints that are available, and how to compute degrees of freedom of a mechanism.